Okay, now let's see one example for applying the Newton's method. Suppose I want to solve this nonlinear function, which immediately you can see is an EOQ problem. Okay, but here let's treat it purely mathematically. So x is the variable and the f is the function. This is indeed nonlinear. Okay, so I can actually see the global minimum, which numerically is around 144, and the graph is here. Okay, so now I'm going to apply the method. So what I know is that at any xk, I need to get its quadratic approximation. So I need to first do the calculation to get my quadratic approximation in general. Okay, so there are a lot of notations, but actually what you are doing is to get the function itself, the first order derivative, which is here, and the second order derivative, which is here. Okay, nothing else. And you need to plug in xk, that's why you have xk here, 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 and here. And then x enters here and here. This is your quadratic approximation. You actually have all those numbers. So if I even give you an x0, which is, for example, 80, then I can plug in all the numbers and get my quadratic function, something like this. Okay? Graphically, it's easier to understand. So I say that x0 is 80, which is here. So this is your x0. Okay? Then I first find the point on the function and then approximate the original function by a quadratic function around the current solution x0. That's the red curve I obtain. Now that's the red curve I obtain. Okay? Then our next step is to solve for the minimum point of this red curve. Okay? So I want to solve the global minimum xk plus 1 by satisfying this equation. Okay? Because I have all these numbers, so I do know what's this curve. So I can do some first order condition, whatever, and to find that my optimal solution here would be this one, x1. From x0, which is 80, I'm going to advance myself to x1, which is the solution of this equation, and that's around 101. Okay, and that's exactly this point. If I do one step further, then I'm going to improve even further. And actually, we don't really need to get that quadratic function again, because we do have our formula, right? From xk, I want to advance to xk plus 1. All I need is the first order derivative and the second order derivative. So if I plug in all the numbers into this formula, I actually can get x2, x3, x4, x5 again, and again. So that's how from x1 I advance to x2, which is here. I get even closer to an optimal solution. Okay, that's how I apply Newton's method to solve this problem. At any point, I look for a quadratic approximation for the original function, and then I get to the minimum point of the function. At that point, I do it again, so that's how I get my blue curve, which is the quadratic approximation along the quadratic approximation of the function around x1, and then I move to x2, which is the global minimum of the blue curve. If I keep doing that, eventually I will get to the bottom of the function of my black curve, which is my original function. It can be shown that if your function is convex, then typically a second order method like a Newton's method can be faster than your gradient descent method, or in many cases. Okay, now we need to generalize our Newton's method for multivariate NLP, but actually it's nothing but changing first order derivatives to gradient and the second order derivatives to Hessian. So suppose f is from n variables to one variable. Then given xk, we want to get the quadratic approximation around xk. You see that first order derivative becomes gradient, and the second order derivative becomes Hessian. Now, previously you have a square term, now you need to do inner product. Notation wise, it's terrible, it's very complicated, but the concept is just the same. Okay, so this is a vector and this is a matrix. This is an inner product, sorry, there should be transpose. So this is an inner product, and this inner product gives you, again, a point, a number. Okay, so we do use the Hessian, which is here. Okay, so that's why this is a second order method. Then we will move from xk to xk plus 1 by solving that equation. Now you remember that we do have an equation, right? And now in the equation, previously it was minus x prime at the numerator and the x prime prime at the denominator. But because your x prime prime now becomes your Hessian matrix, you cannot put a matrix at the denominator. So naturally it becomes an inverse. Okay, and then this is your gradient. Okay, now let's work on this example about two variables. We want to minimize f of x, which is a function of two variables, x1 to the power of 4 plus 2x1 squared times 2x2 squared plus x2 to the power of 4. So again, we can see that the optimal solution is actually 0, 0. Let's see how we may approach it. So again, we can first find the general gradient and the general Hessian, or it should be Hessian. Okay, and Hessian is a matrix which is 2 by 2, so these are standard things we can do. Suppose that we start from a point which is, let's call it BB, or maybe 1, 1 or 2, 2 or whatever. So in this case, let's assume we start at BB for some positive B. Then we can plug in BB into the gradient. We get that our gradient should be 8b to the power of 3. Okay, and the other component is the same. And then if we do it again, this should be Hessian and this should be x0. Okay, if we do it again, and we're going to get our Hessian, which is something like this. Okay, now what we need to do is simply to plug in numbers into this general formula. We start from x0 minus the inverse of our Hessian, and then times our gradient. That's going to give us our x1. So if we plug in numbers, and plug in numbers, we will be able to show that the next point, x1, is 3 over 5b and 3 over 5b. Actually, if we keep doing that, we can see that when k is 2, then we square it. When x is 3, when k is 3, we make a cube. So actually, we can see that when k goes up, indeed we will get closer and closer and closer to 0, 0, which is our optimal solution. Okay, now let's make some remarks and conclusions. For Newton's method, if you recall the whole process, it does not have the step size issue. You don't need to choose any step size because in each iteration, you move to the global minimum of your quadratic approximation. It does not need to solve for an optimal step size, okay, which is something we did for gradient descent, but for Newton's method, we don't need to do that. It in many cases is faster than typical first order methods, because this is a second order method. It uses more information, more properties about your function, so it can be typically faster. For a quadratic function, if you are interested, you may want to show that Newton's method will find an optimal solution in one iteration. So it's not very surprising, right? Because this is a quadratic function. And then you, at a point, approximate this function by a quadratic function. So your approximation will be the function itself. and then you move to there, you're done. So that means you can get to your optimal solution in one iteration, while your gradient descent may need to run for a lot of iterations. So that's why that's one typical example that Newton's method is faster. However, it may be possible that we fail to converge for some functions. In particular, we may move too large, too far, and then go back too far, move too far, go back too far. So it's possible to construct some examples that your Newton's method failed to converge. So that's some danger part about Newton's method. So let's conclude about today's lecture. We gave you some basic ideas about gradient descent and Newton's method. Actually, we have much more algorithms, many more algorithms, and they have different properties, different situations to use them. In general, we need to consider whether a function, whether an algorithm is guaranteed to converge, and in that case, how fast it will converge. Of course, we also need to care about whether it will converge to an optimal point. Sometimes we need to deal with non-differentiable functions. There are some methods that we can apply to non-differentiable functions. We don't have time to talk about it in this course. Finally, there are, of course, constraint optimizations. Also, you may want to think about what's going to happen if you apply gradient descent and the Newton's method to a problem with constraints. That means if you follow the definition of gradient descent and Newton's method, your next point may be infeasible. In that case, what will you do? Well, there are many different methods that tackle this problem, but again, we don't have time to talk about it, and that's beyond the scope of this course. Okay, so that's the end of our discussion about nonlinear algorithms. Thank you.